transformer type designations use letter codes to indicate winding connections. Common types include DY1 DYN, Y, and DD. For DY1, D indicates a delta-connected primary winding, Y indicates a star or Y-connected secondary winding, and 1 signifies no phase shift between primary and secondary voltages. For DYN, D indicates a delta-connected primary winding, Y indicates a star-connected secondary winding, and N indicates a neutral connection grounded on the secondary side. Other type designations include GI, which represents star-connected primary and secondary windings, and DD, which represents delta-connected primary and secondary windings. Psi represents a zigzag-connected primary winding with a star-connected secondary winding, and INT represents a star-connected primary winding with a grounded neutral and a delta-connected secondary winding. The primary winding is connected to the input source of electricity, while the secondary winding is connected to the output load. A delta connection involves connecting the 3 phases in a loop, forming a closed path. A star connection involves connecting the 3 phases at a common point called the neutral. A Z connection involves connecting the 3 phases in series with a phase shift of 120 degrees. The type of transformer connection determines firstly the voltage and current ratios between the primary and secondary windings, secondly the power factor of the transformer, thirdly the grounding arrangement of the windings, and fourthly the ability of the transformer to handle unbalanced loads. Delta connections are often used where a stable voltage supply is needed, and they can handle large unbalanced loads effectively. SAR connections are commonly used for distribution transformers and can provide a neutral point for grounding purposes. Zigzag connections are used to reduce voltage unbalance and harmonic currents. The selection of the appropriate transformer type depends on the specific application requirements and the characteristics of the electrical system. Understanding these connections and their implications is crucial for proper transformer selection and operation. Choosing the correct transformer type can significantly improve system performance, reliability, and safety. For example, in applications where a ground fault is likely, a DYN transformer can provide a path for fault current to flow, helping to protect equipment and personnel. The neutral connection in a DYN transformer is grounded to provide a reference point for voltage and to limit the voltage rise during fault conditions. In contrast, a DY1 transformer does not have a grounded neutral, which may be suitable for applications where ground faults are less likely. In distribution systems, Y transformers are often used because they provide a stable neutral point and allow for easy grounding. They are also relatively simple to construct and maintain. DD transformers are less common in distribution systems but may be used in specific applications where a delta connection is required on both the primary and secondary sides. The Z connection is a specialized connection that is used to mitigate harmonic currents and voltage imbalance. It is often used in applications where there are significant nonlinear loads, such as adjustable speed drives and rectifiers. The INT connection is used to provide a stable neutral point and a delta connection on the secondary side. This combination can be useful in applications where both a grounded neutral and a high fault current capacity are required. In summary, the type of transformer connection is a critical factor in the design and operation of electrical systems. By understanding the characteristics of different connections, engineers and technicians can select the appropriate transformer type for a given application and ensure the reliable and safe operation of the system. When selecting a transformer, it's also important to consider the voltage and current ratings, the impedance, and the insulation class. The voltage and current ratings must be appropriate for the application, and the impedance must be chosen to limit the fault current to an acceptable level. The insulation class must be high enough to withstand the operating voltage and temperature. Regular maintenance and testing are also essential for ensuring the continued reliable operation of transformers. This includes visual inspections, insulation resistance testing, and turns ratio testing. Transformers are designed to operate efficiently and reliably for many years, but they can be damaged by overload, overvoltage, and other abnormal conditions. Proper protection devices such as fuses and circuit breakers should be installed to protect the transformer from these conditions. Furthermore, the location of the transformer should be carefully considered to minimize the risk of damage from environmental factors such as moisture and extreme temperatures. In addition to the winding connections and other electrical characteristics, the physical construction of the transformer is also important. The core of the transformer is typically made of laminated steel, which is designed to minimize eddy current losses. The windings are made of copper or aluminum and are insulated to prevent short circuits. The transformer is typically enclosed in a steel tank, which is filled with oil to provide insulation and cooling. The oil also helps to dissipate heat generated by the core and windings. The design of the tank and cooling system is critical for ensuring that the transformer can operate at its rated capacity without overheating. The cooling system may include radiators, fans, or even a water-cooled heat exchanger. The selection of the appropriate cooling system depends on the size and rating of the transformer and the ambient temperature. The transformer must be sized correctly for the application. An undersized transformer can overheat and fail, while an oversized transformer can be less efficient and more expensive. The transformer's loading should be continuously monitored to ensure it is operating within its rated capacity. If the transformer is overloaded, steps should be taken to reduce the load or replace the transformer with a larger unit. Transformers play a critical role in modern electrical systems, and their reliable operation is essential for ensuring the availability of power to homes, businesses, and industries. By understanding the principles of transformer operation and maintenance, engineers and technicians can ensure the safe and efficient use of these important devices. When troubleshooting transformer problems, it is important to follow a systematic approach. Firstly, check the voltage and current on both the primary and secondary sides of the transformer. Secondly, inspect the transformer for any signs of damage, such as oil leaks, cracked insulators, or burnt windings. Thirdly, use a multimeter to check the resistance of the windings and the insulation resistance between the windings and the core. Fourthly, if the transformer is equipped with a tap changer, ensure that it is set to the correct position. Finally, if the problem cannot be identified through these steps, it may be necessary to perform more advanced testing, such as frequency response analysis or dissolved gas analysis of the oil. Proper grounding of transformers is essential for safety and for preventing damage to equipment. The grounding system should be designed to provide a low impedance path for fault current to flow back to the source. The grounding conductor should be sized according to the National Electrical Code, NEC, to ensure that it can safely carry the maximum fault current. Transformers are subject to various standards and regulations such as the National Electrical Code (NEC) and the National Electrical Safety Code (NESC). These standards specify the requirements for the design, installation, and maintenance of transformers. Compliance with these standards is essential for ensuring the safety and reliability of electrical systems. In addition to the traditional oil-filled transformers, there are also dry-type transformers. Dry-type transformers use air as the insulating medium and do not require oil. They are often used in indoor applications where there is a risk of oil spills. Dry-type transformers are typically more expensive than oil-filled transformers, but they can offer several advantages such as reduced maintenance and environmental concerns. The selection of dry-type or oil-filled transformers depends on the specific application requirements and the preferences of the owner. In conclusion, understanding transformer winding connections, types, maintenance, and troubleshooting is crucial for electrical engineers, technicians, and anyone involved in the design, installation, or operation of electrical systems. It ensures efficient, reliable, and safe power distribution.